Thank you. I want to show you a protocol that aims at preserving privacy. And what do we mean by preserving privacy? And privacy preserving basically means we want to protect data. But we're not focusing on the data that gets transmitted in the protocol. We're focusing on the data on the control plane. More specifically, we call this the network configuration, and that's the data, how the network is set up, so where are links in the network, and how are they configured, and how are the routers configured. So you might ask yourself, why would you want to do that? In an age where every information that you transmit on the internet gets processed and analyzed by all kinds of agencies, you might want to rethink your willingness to share information. Because after all, networks are very interesting and attractive targets. Because once you have access to a network, you can read all the information that gets transmitted, and so it's not only interesting for the NSA, it's also interesting for hackers. And if you know the information how a network is set up, it's a lot easier to attack than if you protect this information. And a very different angle is you could cooperate better. So if you've got two ISPs, they're competitors, so they might not be willing to share information about how they run the network. But if they would, you could achieve better results in routing. So you might think we already have this. There is a property called information hiding, and BGP especially has this property. But hiding is not protecting, so there's a very specific difference. If you hide something, you can find it again. So, and what we're aiming to do is protecting information. So even if you look for it, you can't get it. The other important thing here is this information hiding is in BGP because the network providers want this to be. So there's a need for hiding information, and I think we can do better. And our underlying idea is, why don't we use cryptography? And it has shown that it works to protect data, so why don't we use it in this case? And the tool of choice for our protocol is called homomorphic encryption. And the basic idea of this encryption is you can encrypt data, give it to someone else, and he can do computations on these encrypted values. And a bit more formal, so you have a public key cryptosystem. If you know what public key cryptosystem is, you have public keys to encrypt data and secret keys to decrypt the data. But it also has this property that there is an operation on encryptions that relates to an operation on plain text. And what we're using is a so-called additive homomorphic encryption system because it allows you to do additions. And more specifically, what we're using in our protocol is called secure sum. The setup is pretty simple. You have different parties here, four in this case. And the last one, the green guy over there, he wants to know the sum over all these X inputs. But the other parties involved don't want to share this information, they don't want to tell it. So how would they go along? Well, they use homomorphic encryption, so it's a linear protocol from the, what is this, left to the right. So our blue guy encrypts his input with the private key of the green one, sends it to the orange guy. He uses now the homomorphic property to add his input to the encryption. This goes down until it reaches the green one. And now, because he has the secret key, he can decrypt those values, he can add his own value, and he learns the sum. And the important thing, he only learns the sum. He has no can't learn any more information about those other inputs unless you would collude with one of those guys. The basis of our protocol is the distance vector protocol, and I know we're in a networking conference, and I'm pretty sure you all know what distance vector routing is, but I still want to show it quickly because to introduce the notation we use for our protocol. So we've got this toy network here with routers, and they're connected with links, and links with weights, and shortest path in the network is the path. So you add the weights of the links in the path, and that's the distance, and you're looking for the shortest distance between routers. And routers have routing tables with destination, then the next hop to this destination, and the distance in it. And so if now a new router comes up, here in this case the green one, its neighbors notice that, and they start creating what they call announcements. An announcement contains the destination router. In this case, they tell you, I know the path to the green guy. This path costs 3 or 8 systems. And also the next hop, how to reach the path. And they share this information with their neighbors. So, and now, if a router like the blue one here gets those announcements, he has to make a decision on which path he wants to choose. And he does this by adding the cost for the next link and choose the shortest one, and in this case it's the one over the yellow router, and puts this in his router here. The important thing to remember here, it's a two-stage process. You have this reachability, the sharing of the reachability information that was sending out those announcements. And the second part is that making a routing decision, making a decision which one is the path, what do I want to use. And our protocol uses the same principles. So a router comes up and we create announcement messages. But now what we want to do is protect the configuration of the network, and in this case it's the weights on the links. That's what we want to omit for anyone to learn. And also, okay, so if we now create those announcements, we can't send the distance with it because it would reveal the configuration. So we just send this blank messages around, only telling someone, I know the path, but not how expensive it is. So, and if the blue router here now gets those announcements, he has a problem because he can't make this decision on the spot which of those paths is the shortest. So our idea now is to send probe messages along all of the announced paths, and along the way we compute the secure sum to get a measure of the distance, and then the destination router makes a decision for us which one is the shortest path. So we call this process a shortest path computation, and it starts by creating those requests. And the request basically contains, again, the destination in green, then the weight or distance of the next link, but it's encrypted with the public key of the green router. Only the green router can eventually decrypt this value. And then we also add some randomly generated labels there, and I will tell you in a minute what they're for. So those packets then travel along those announced paths to the destination, and every intermediate router now, when he gets one of those requests, he has to, first of all, create a temporary routing table, matching those random labels to the link they came in, so that the response can travel back through the network. And in the next step, they have to add the weight of the next link in the path. And they can do it by using the homomorphic encryption that we saw earlier. So, eventually, those probe messages reach the destination, and since he got the decryption key, he can decrypt the values of the distance, find out which one's just the minimum, and then create response packages. And these response packages basically just contain the random label to get back to the originator, and then the label of the path that's the shortest. In this case, it's the purple one. So they travel back, and since we've got these temporary routing tables on the intermediate routers, they know how to send the information back, and it will eventually come back to our blue router, and he then analyzes these packages and sees where the purple path was the shortest one, and the purple one was the one over the yellow router, and can put this in his routing table. So that's the basic idea of the protocol. It's a bit more complex, but I want to refer you to the paper if you're interested. But the basic idea is basically clear, but it's this. And to give you an idea of the privacy preserving part, well, we basically just did this secure sum over the routes. So no intermediate router could learn anything about those weights because the information was encrypted and only the destination router, the green one here, could decrypt. And we used those random labels so that the green router couldn't connect those values to anything sensible in the network. If we would have said the address of the blue router, then he could match that and infer information. So that's why we use random labels. And the protocol has some more interesting properties. For a start, because we do basically with this probing, we confirm that this path actually exists. So we don't have problems like loops or count to infinity, because you only select a path if it's actually there. And in the ideal world, it converges. Basically, it behaves exactly like a Bellman-Ford algorithm, so you could use the same argument. But the problem comes with the real world. So in the real network, messages can be dropped, routers can be down, and therefore we had to introduce timers in our protocol so that we can't wait forever for a packet to arrive if it gets lost. So there are timers in there, and with these timers, it's really hard to tell if protocol converges. You can easily construct cases where it won't. So if you choose the timers too short, then and you don't give the packets the time to travel along the path to the destination and back, then you wouldn't get an optimal solution. However, we did a lot of simulations and emulations of our protocol, and we never ran into problems if we choose the timers in a sensible way. And there's a lot in the paper about evaluating how you have to choose the timers. But the more interesting bit is how does our protocol compare? Because it seems it seems very involved compared to normal distance vector protocol. So you have a lot more computation to do because now you have crypto. But really, since CPU is now a Sochi, the computational aspect is not that bad. But let's look at convergence time first. So here on the x-axis is the size of the network, y-axis is the convergence time, and we compare our protocol to standard spectrum protocol. So the solid lines is distance vector, and the dotted line is our protocol. And well, we choose here those Renyi graphs and Arabasi graphs, and we know they're not very realistic, but in a sense, they represent two different extremes in the networks. Just to give us an idea, what you can see here is that our protocol behaves a bit worse than the distance vector protocol, but it seems to be a constant offset. So it's not that bad of a price you have to pay to gain these privacy properties. And the other thing to look at here is the number of messages. Since our way of computing shortest path, it was creating a lot of messages. And again, we have an x-axis the size of the network, and y-axis now the number of messages in 10,000. But the good thing is our protocol creates almost the same amount of announcements as a normal distance vector protocol. But now we also add those requests and replies, and as you expect, you get a lot more the bigger the network gets, because the path in the networks gets longer, so you have a lot more messages. But again, we think it don't have to be that big of a problem, because network links are now at these high capacities compared to when we first thought about distance vector protocol. And it might be a price you're willing to pay. However, it looks like it doesn't scale very well, so it's not a good option for really big networks. Yeah, I guess I have some time. Let's conclude. The important thing is you can actually do this. We've shown this. You can protect, you can find a routing solution in the network without having to share all those configuration information. And the other important thing is, although we used a very simple protocol to base it on, standard distance vector, our technique is not limited to it. So you could easily extend this to more complex routing protocols. You could think of lexicographic protocols. And we implemented all of this. There's a simulation and an implementation. You can download it. It's freely available, and I want to encourage you to play with it and push it further.